Welcome to AI driven perception, learning and mapping for drones. This particular lecture we are going to talk about operations of convolution neural network. This lecture covers CNN architecture, convolution operations, extending the polling operations. Then there is something called padding, stride. How do we process the multidimensional input? If you remember in the previous lecture, I brought the digit recognition problem and then I introduced basic convolution operations and I show how the convolution operation reduce a 5x5 image, matrix to 3x3 for a 3x3 filter, right? But I don't want to reduce the size. Spatial precision should not be lost. What should I do? How do I maintain? We saw for one dimensional input, right? But any image is the RGB, right? Red, green and blue, or sometimes it could be a hyperspectral image comes into picture. If you have a spectral information, not necessarily 3-dimensional, it could be multi-dimensional input. When you have multi-dimensional input, how do you process it, right? Is the convolution operation is complex? How do you represent them as a linear operation, right? How do you understand the depth and standard architecture is the focus of this particular lecture, right? Now, spatial network, we talked about it, right? Convolution operation is systematic way of extracting local features inside the image. We talked about this convolution operation in the previous lecture. There is an image I, there is a filter, there is a small patch where the filter is applied to extract informations, right? We talked about pooling operation too. There are different type of pooling was there. Max pooling, average pooling. What the pooling does? It compresses the feature map while keeping the most important information. Think about it, I am just using this for satellite image. A large area image is there. I want to compress that information. If I want to segment the large area satellite image, what I meant satellite, you remember when we talk about loss function problem, we showed that hyperspectral image is there, every pixel belongs to a specific class, whether it is a grass, water, is an urban area and so on and so forth. And if you see a hyperspectral image and you say a resolution of this image is 30 centimeter cross 30 centimeter and you are talking about a building, think about how many pixels representing the building itself, right? So I want to reduce the dimension so that I can process, I can go into the pooling, right? So it gives a kind of a presence of local feature is there and the maximum information I can read or average information I can read, right? So it kind of reduce the dimension and robust against a translation and preserve the feature, presence of the feature, right? I can use that. Now, understand this convolution operation, shrink the size. For example, I have taken a matrix of 6x6 and I put a filter of 3x3. See, earlier I just used 1 and 0, but then I just want to give the pixel itself, right? So if I consider the convolution operation, first patch, first 3x3, multiply by 3x3 filter, right? 3 into 2, 7 plus 7 into 4 plus 2 into 1, that's a first row, 6 into 3, 4 into 5, 9 into 2, that's a second row, plus 1 into 1 plus 8 into 3 plus 5 into 1. That's the convolution operation we are talking of, right? Which results in 137. That's the first value. I slide the patch and do the operation again. Slide it further. Finally, I get activation map. The size of the activation map is 4x4. I have taken a 6x6 matrix and reduced to 4x4. That's what I meant convolution, shrink the size, right? Now I don't want the size to be reduced. What should I do? There is something called padding. I pad the image which is 6x6 with a 0 one row of 0, I mean top one row, bottom one row, in this left and right column zeros. So I padded with zeros. Now the size has increased from 6 cross 6 to 8 cross 8. I run the same filter 3 cross 3. What will happen? I am retaining the structure of 6 cross 6 output itself. Input image is 6 cross 6, output is also 6 cross 6. So by adding padding, I can avoid the convolution operation shrinking the size, which means I can retain the spatial precision, right. Now instead of 6 cross 6, if I put a 5 cross 5 filter, then that will shrink even further. In that case, what should I do? Instead of 1 rows of 0, I may have to put 2 rows of 0. So the size, instead of 8 cross 8, now it has become 10 cross 10. With the 5 cross 5 filter, I can still get 6 cross 6 output. If I put a filter size increases, the radius needs to be padded with more and more layers of zeros so that I can extract the information, retain the same input size image, I mean same size of the image. So we know if you reduce the activation map dimension, right, you have a higher resolution, you want to reduce the resolution, right. How do I reduce? One is I can do pooling, but other way is I don't want to slide 1 pixel by pixel. I can stride. Stride means how do I stride? 1 pixel or 2 pixel. Same convolution operation, but the larger image. So I want to stride by 2. First what I do? I take the first 3 cross 3 pixels. The next one I shift by 2 and take this pixel and operate. So if you want to understand, it will be easier here. See, when I do this, I jump by 2 pixels down and create the activation map, right. So you can have stride also, you can use to reduce the dimension of the image to smaller when you have high dimensional image, 1K resolution. Why do we need the stride? Because there are many pixels representing the same feature space. There is no additional information I will be gaining. In such cases, you can use the stride operation to extract the local features. Okay. Now, how do I compute the feature map? Right? How do I decide when you have padding, when you have a stride operations and all this, what should I do for a feature map? Right? What we are talking of, there is a convolution operation, there is a padding operation, there is a stride operation. With that, I want to create a feature map. How do I fix the padding size or stride size and all that for a given filter size, right? Let us say there is an image n cross n, size is n cross n, right? And I have a filter which is going to be f cross f, right? The filter size is f. But then I want an output image whose dimension is equal to n itself, right? So what I can do, I can choose the values of p and s such that the resultant feature map dimension is same as n cross n. So how do I mathematically represent this process? The feature map size is nothing but n plus 2p, where p represent the padding, right, minus f is a filter, right, divided by s plus 1 and you do the flooring operation. That defines. So if you want to keep, let us say 6 cross 6 is my input, my n is 6, right. So n is 6. What is my filter size? F is 3. Now I want to find out what should be my P and S such that the feature map is also 6 cross 6, right. So what we are talking of, 3 plus, I don't know the p value, we'll just keep it as it is, p minus 6 plus 2p minus 3 by s plus 1, right. We are going to stride by 1. Let us say s is equal to 1. Then what happens? 3 plus 2p plus 1 is my one dimension, which is what is that? 4 plus 2p, right. What size my features map should be, or activation map should be? It's same as that of input image. It should be equal to n. What is n here? 6. So 4 plus 2p equal to 6. From there we can identify I need to do the padding of 1, right. So you can decide based on input image, based on the filter size, based on is a high resolution image or what you want the stride operation, you want how the S going to be. With that you can find out what should be the padding, so that the resultant feature space activation map is extracting the local feature with the same precision, right. Spatial precision you can retain it. Now I can do the same thing for a multi-dimensional input. For every dimension you could have a filter, right. So earlier we talked about single dimension, right. Suppose if we talk about RGB image, for R there will be a matrix, for a G there will be a matrix, there will be a B, there is a matrix. So when I say 3 cross 3 filter, what I meant is for every dimensional input there will be a one filter. So it will be 3 cross 3 cross 3, okay. That is my filter, but still we call it as a 3 cross 3 filter, okay. For every dimension there is a 3 cross 3. If there are 3 dimensions, it will become 3 cross 3 cross 3. That is how it is, right. I can get 1D activation map. For every dimension I multiply and sum all of this, and that is my activation map. I can do that, right. So if I am trying to generalize the architecture, if the input image is 128 cross 128, this is a single channel, I am going to put a 4 different filters. Each filter is 28 cross 28, right. Then I need a 4, each filter will give one activation map, there will be 4 activation map, but I want to retain the size as it is. Input size is 128, the activation map size also 128. What we are trying to do, every filter is searching for, is there a presence of 0 in the entire image? Is there a presence of 1? Is there a presence of 2? Is there a presence of 3? And that is how it is searching. And finally it produces an activation map of the same size. Where is this number 3 present in the entire input image, right. That is how it sees, right. Now instead of black and white, if I talk about RGB image, it is the same. Remember, I want a 4 filters. Each filter is, instead of 3 cross 3, it will become 3 cross 3 cross 3. For every channel there is one filter, right. There are 4 such filters that I wanted to have, so that I can process the image and I can have 4 activation maps, right. That is how it represents in the multidimensional space, right. I can have activation map for every dimension, or I can merge the dimension, make it as a single dimension also. That is a possibility, right. So if I am trying to do hyperspectral image, there are n channels, right. What we say n filters, a filter size is f cross f. We do not add that number of channels explicitly, just have to understand that that is what it represents. How many filters that you want, that is the filter, and it will become number of channels and what is the dimension of the filter of every channel. That is how we represent, and we can have f activation map, right. We can reduce all the n dimensional input to a single dimension, or you can still retain the n dimensional based on what we wanted to extract from every dimension is, right. Now, when the dimension increases, it looks like a very complex operation. If you look at mathematically, convolution operation is a very simple linear operation, right. It is just a linear operator with a special structure being there. You see here we have 3 into 6 cross 6 tensor. What I meant is there are 3 channels, right, and each channel has 6 cross 6. That is means each channel has 36 pixels and there are 3 channels. I have a filter, the size of the filter is 6 cross 6, right. I have to put for 3 channels, every channel. So, totally I will have 27 numbers, right. I want to have an activation map whose size is going to be 4 cross 4. I am not going to pad anything, just for you to understand the whole process here, right. Now, this is my structure. How do you visualize this convolution operation? If you see, I can represent every filter, right, in a row, right? Filter 1, filter 2, filter 3. You can represent the filter in a row. In an image, you can take how much ever patches being present and you can represent each patch as a vertical column, right. If you see, the convolution operation is nothing but matrix matrix multiplication, which results in activation map. Okay. So, if you just have to put it in that sense, if you see whatever the filter, the first filter 2 4 1 3 5 2 1 3 4, I am just representing as a one row with that filter information. There are 3 filters, filter 1, filter 2, filter 3 for 3 channels, right. Now, what we are doing, we take the first channel, we are representing the patch. What happened? 3 7 2 6 4 9 1 8 5, I am just representing like that, right. So, I get the activation, right. So, every channel can be represented that way, so then you get the output, right. In a summary, what we are introduced here is we understand the new operators like a padding, stride, with that how we can retain the structure of the activation map, how we can bring in multiple channels and how these channels are represented to extract the information from convolution operations. Thank you.